Welcome to this session on the recirculating aquaculture system, or RAS. This course will introduce you to the basics of RAS, its key components, and why it is a critical system in modern aquaculture. We will look at various relevant definitions of RAS based on recycling degree, water replacement per day, and water replacement per day per fish feed given to the fish. We will also look at two main types of RAS design setups depending on the stage of the fish development. So, what exactly is RAS? RAS stands for Recirculating Aquaculture System. RAS is an example of an intensive aquaculture system where aquatic organisms such as fish are raised in tanks and the wastewater from these tanks is collected, treated, and returned to the fish tanks. This allows for the water to be reused multiple times, making it a highly sustainable option for aquaculture. How is RAS able to maintain optimal water quality? RAS utilizes several water technologies to maintain optimal water quality. These water technologies include oxygenation, CO2 removal, pH regulation, mechanical filtration, and biofiltration to maintain optimal water quality. From this graph, we can notice that the higher degree of recirculation will require several water treatment combinations to achieve optimal water quality in the fish tanks. In RAS, only a small amount of new water is required or replaced. Why do we need new water in RAS? Even in an intensive system like RAS, new water is necessary to ensure that the system maintains balance and the fish remain healthy. The two main reasons for bringing new water into RAS includes the following. 1. To compensate for the water loss to evaporation. 2. To help remove waste product from the system, preventing the accumulation of toxins which could harm or kill the fish. What are the key components in RAS? In general, RAS is composed of several key components, including 1. Fish tanks, where the aquatic organisms are held. 2. Mechanical filtration systems help to remove solid waste, such as uneaten fish feed and fish feces. 3. Biological filtration systems help to break down dissolved organics, such as organics and ammonia. CO2 degassing units remove CO2 from the water and help to maintain gas pressure in the RAS. 5. A circulation water pump is required to keep water flowing through the system. 6. Oxygenation systems ensure that the fish have sufficient oxygen. 7. The new water inlet system helps to replenish any lost water due to solid waste removal or evaporation. 8. pH regulation buffers ensures optimal pH is maintained in the fish tanks. 9. Drainage systems help to remove waste when necessary to control toxic concentration levels of contaminants. What are the relevant definitions of RAS? There are several ways to define the recycling efficiency of RAS. One important concept is the recycling degree, which is often expressed as a percentage. Another concept is water replacement per day, also expressed in percentage. The last concept compares water replacement per day to the amount of fish feed given to the fish in the RAS system. We will use this example to understand how various definitions come about and are estimated. In this system, we have a fish tank volume of 1000 cubic. Water in this tank is changed twice every hour, resulting in 2000 cubic an hour RAS water flow rate. We also have a total water treatment system sump water volume of 500 cubic. Note that inlet water flow rate is equivalent to the drain water flow rate, assuming evaporation is minimal and negligible. To determine the recycling degree in percentage, we will refer to our RAS setup example. Here, only water flow rate will be used without considering fish tank volumes or water treatment sump volumes. Recycling degree in percentage is calculated by dividing the RAS water flow rate by the total of flow rate of RAS and inlet water. This will translate into QRAS over QRAS plus QIN times 100%. This gives us 2000 cubic an hour divided by 2010 cubic an hour in percentage. Therefore, the recycling degree of our RAS example will be 99.5%. In this case, we can say our RAS is recycling 99.5% of water while bringing in and discharging only 0.5% of water. To determine the RAS replacement per day in percentage, we will refer to our RAS setup example. Here, both the water inlet flow rate and the total RAS system volume will be considered. To calculate the water replacement per day in percentage, we will express water inlet flow rate in daily terms. We will convert the inlet flow rate from hourly rate to daily rate and divide that by the total water volume in the RAS. The total RAS volume is the fish tank volume plus water treatment volume. We will multiply the inlet water hourly rate by 24 hours per day to get the daily rate. This daily rate will be divided by the total RAS volume. This will translate into 240 cubic per day divided by 1500 cubic times 100%. This will give us 16% water replacement per day. This means 16% of the RAS water volume is changed every day. To determine the water replacement per day per kilogram feed, we will again refer to our RAS setup example. We will assume we are going to feed our fish daily with 250 kilogram fish feed. In this calculation, only the new water added to the RAS and the fish feed given to the fish are considered. Our inlet water flow rate will be converted to a daily rate by multiplying our hourly rate by 24 hours per day. This daily inlet water flow rate will then be divided by the daily fish feed given to the fish. When both days are cancelled, we will be left with 240 cubic per 250 kilograms of feed. Therefore, the water replacement per kilogram of feed will be 0.96 cubic per kilogram or 960 liters per kilogram feed. In some cases, when the feed conversion rate or FCR is known, you can inversely calculate how much weight of fish is produced from specific amount of water available. We will look more into this topic in the future. There are different types of RAS systems depending on the stage of the fish development. This includes 1. Hatchery and juvenile RAS system. 2. On-growing RAS system. Hatchery and juvenile RAS systems are designed for broodstock, egg hatching, fingerlings, or smolt production. They are designed for the early stage of fish production. If raw stock are held, then eggs are produced from the fish in these systems. The characteristics of a RAS designed for hatchery and juvenile includes the following. 1. These systems have low water consumption. 2. These farms are smaller and require less area and volume. 3. Fish in these systems are very sensitive. 4. Because they are sensitive, advanced water treatment systems are required. 5. Biosecurity is necessary to prevent any introduction of disease-causing pathogens. 6. This system has less fish density and therefore produces low solid waste. On-growing RAS systems. On-growing RAS systems are designed for bigger sized fish, tabletop size or post-smolt fish production. The characteristics of RAS designed for on-growing fish includes the following. 1. These systems have high water consumption. 2. Farms are bigger and more volume is required, resulting in bigger fish tanks. 3. Fish in this system are less sensitive and are tolerant to harsh conditions. 4. Less advanced water treatment systems are required. 5. Biosecurity is still necessary to prevent any introduction of disease-causing pathogens. 6. High solid waste is produced from these farms. In summary, the recirculating aquaculture system, RAS, is a sustainable, efficient method for aquaculture. It minimizes water use while maintaining a healthy environment for aquatic organisms through advanced filtration and water treatment processes. RAS can be defined based on recycling degree, water replacement per day, and water use per fish feed input. RAS is also designed with consideration to the developmental stage of the fish. Thank you for your attention. Bye for now.